Mhm.
Okay. So it's a pleasure for us to virtually host Celine Zwikel from TU Wien, who is going to give us a talk on symmetries and at null boundaries.
Thank you very much, Miguel, for the invitation. I'm very happy to talk in Paris, I mean, at least virtually. And today I want to talk to you about a couple of projects that I have been doing with several people. So there is Hamed Adami, Daniel Grumiller, Shaheen Sheikh Jabari, Saïdeh Chagendian, Vaid Tagilou, et Hossein Yavatarno. So what is our main goal? We want to determine the phase space of gravitational space-time with boundaries. Why is it interesting? And I give here a couple of examples of boundary in gravity. So for example, you have a asymptotic boundary, for example, future null infinity, which is the boundary of asymptotically flat space-time. You have also another kind of boundary, which are the causal boundary, and for example, the horizon of the black hole. So they have region where they separate two disconnected regions. So for example, in the case of the black hole, the interior of the black hole and the exterior. And why we are interested of describing those surfaces? I mean, there is tons of reasons, and I mentioned a couple of them. So one of them obviously are the holographic dualities, where it is conjectured that the bulk physics is encoded on the boundary of the space-time. And yeah, so that's one point. Another point that might be, I mean, the study of boundaries might be useful is the entropy problem. So we know that black holes have an entropy, but it's not clear yet exactly what are the microstates that account for that entropy. And they might be maybe placed on the horizon of the black hole. There are some proposal about it. So it's interesting to see how to characterize that surface. Also, you might see what happens if you throw something in the black hole, where the information goes. Maybe it's going on the surface, that is this particular region. Once again, it might help on those questions as well. And in another area, there is the gravitational memory effect, where if you put two detectors at the boundary of asymptotically flat spacetime, so at Sky plus, and you put a pair detector, and those after gravitational wave half pass might have a persistent deformation on their position. And so yeah, so that's a bit of the general motivation, why it's interesting to study those surfaces. And what we want to do is we want to describe what is the phase space. And so the phase space here, I mean, what I have in mind is states such that they will respect the boundary structure that I have put. So essentially what I have that in mind is the behavior of the field in the boundary, and also such state that there are solutions to a certain theory. So you have to give the dynamic in the bulk. And to describe the phase space, we need to organize the states in the phase space. And for that, what is important is to consider the symmetry group that preserve the boundary. So you know that general relativity is diffeomorphism invariant, but once you put a boundary, you might break this full diffeomorphism invariance. It means that there are some diffeomorphisms that now will be forbidden because they will break this boundary structure that you have put in your spacetime. So there are not symmetries anymore. And in the diffeo that preserve that structure, you will have two different types. The one who really have pure gauge, really true symmetry, when you act with them, they don't change the states in your system. So you really call them pure gauge. And you have another type of symmetry where they preserve this structure that you have put on your boundary, but they will, if you act on them on a state in your theory, it might change the state. And we call them large. And so that's the symmetry we're gonna consider. And in this talk, and I want to talk about the null hypersurfaces, like such horizon of black hole, or for example, And so we want to study this phase space. So what I'm gonna do, first I will look at what I'm expecting to find in the phase space. So I will make a counting of the degrees of freedom that I'm expecting. And that counting was argued on this essay that we wrote for the gravitational foundation. I forgot the name. Anyway, so that's is in this essay. And after, I will more detail the program that we have established to study this question in full details. And that is in the paper that has been put out 2 months ago. Finally, I will first illustrate the first step of this program on the 3D gravity case. And at the end, I will also talk on some aspect on the 4-dimensional case, where part of it is in a paper that has been out 6 months ago, and also on ongoing work that we are doing. And finally, I will conclude. So please stop me anytime you have any question, and yeah, let me know if something is not clear. So in pure gravity in D dimension, with the boundary, you have the field are a metric who has dd plus 1/2 component. And out of that, you can gauge fix d of them, that obviously preserving this boundary structure. In there, you have also d minus 3/2 component correspond to propagating degrees of freedom. So that I will refer to as bulk degrees of freedom. And those, you cannot remove them by a change of coordinates. They are really physical degrees of freedom. And if you do the computation, you're left with d component that will correspond to the boundary degrees of freedom. So as some function that they are free on the boundary that you can use still. And I mean, that's why I use the word residual. And as they're living on the boundary, they will be codimension 1 function. And yes, so when you put a gauge, you have to pay attention of not killing. I mean, if you're interested to the question of studying the most general boundary condition, to describe the boundary degrees of freedom, you have to pay attention on the gauge you put, because you might kill some of the boundary degrees of freedom, and we will see that more explicitly during my talk. So we wanted to study systematically these boundary degrees of freedom on a generic surface in the bulk. And so we don't want to put boundary condition. We don't want to impose extra structure, because we want really to describe the maximal setup. So that's the first question we ask. And after, we want to understand what they represent, those boundary degrees of freedom, physically speaking, and also how can be the interaction between the bulk degrees of freedom, so the graviton, and the degrees of freedom that living on the boundary. And as often in physics, it's nice to start by a simple setup, but yet interesting, which is 3-dimensional Einstein gravity. Why so? Because in 3D gravity, there is no local degrees of freedom, so no graviton. You can just turn on boundary degrees of freedom. And it's interesting because it's not a trivial theory. You have black holes and different structure in there. So that's what we're gonna do. It's to study the 3D gravity. So for the counting I gave you at the beginning, we are expecting that we can find at most 3 codimension 1 function on our phase space. So I have chosen some coordinates. So I decided to put my null hypersurface as a coordinate r equal to 0 here. I have a coordinate that's running along this null hypersurface, which is, I call it advanced time. It's not really a time because it's on the null hypersurface, but just it will be easier to say it like that. So that's the v coordinate. And after, you have also the last coordinate that is the periodic coordinate phi, that is the angle. So that's making the S1 that you have in 3 dimension here. So I choose a certain gauge. And so the boundary structure that I give is the following. So it's similar to the, so you see you don't have term in G and JRR nor JR5. And the term between the advanced term and R is just a function of V and phi. And all these other functions, big F, little f, and h, are function of all coordinates. And I expand them in power of R. Because I'm in 3D, I can solve the equation of motion exactly, but just for the readability reason, I didn't write all of the subleading here. And as I want to have a null hypersurface at R equal to 0, I have to impose a condition on F0 here, the big F0, and it's related to the little F0 and omega. Also, I want that omega to be non-zero in order to not have a degenerate metric. So that's the coordinates. And so now, as I was telling you, we look at the symmetry that will organize the phase space. And so we will look at symmetry that will preserve that boundary structure. So we're looking at vector such that when you act on the point of the phase space on little j, this stuff, it's still on the same form. It's still falling in the same behavior that I gave it to you. If you solve those equations, you will find that this vector in general depend on 3 functions, so t, w, and y. All of them are function of all coordinates, are function of codimension 1 coordinates on the time and the angle. And so you can see that t here will generate translation along the v direction. Y will generate the rotation along the angle coordinate, and W is the wave transformation. So that's the one that's dilatation along, that's expanding your surface.
Sorry, Celine, I missed the beginning of your talk.
Yeah.
Is it the surface you're looking at a boundary of something, or is just some null hypersurface that you've chosen inside some space-time?
It can be, so it's a null hypersurface in the bulk. So I'm not talking about asymptotically surfaces, and it can be any null surface. It can be an horizon, but it can be any null surfaces.
Okay, thanks.
And so they are not exact Killing vectors, so they are modifying the function that you gave in the expansion. And I gave it just 2 examples so you get a sense of what it is, and I don't put a lot of formula for nothing. So for example, this eta, that is the term that was between V and phi, will transform in such a way. And another interesting one to look is this F0. So F0, just let me go back, was the term here was related to the co-rotation of the horizon. Here you see that F0 is this term here, so it means that the horizon, the null hypersurface, we are not using coordinate that co-rotate with that null hypersurface. And if you look at this transformation, you have the following. If you ask now that you are in the co-rotating frame, so it means that you impose that F0 equals 0. What does it imply? So if you put F0 here, you just have this term that is left. And so because you ask that F0 equals 0, you have to preserve that condition. It means that your y, instead of being a function of 2 variables, become just a function of the angle. So you lose a bit of symmetry going to this co-rotating frame. So, but here we don't do that. We keep it very general. And so now that I have the symmetry, I can look about the algebra of those symmetry. And I don't use the Dirac bracket, but rather this adjusted bracket. And because this bracket will be relevant when we look to the chart, so just, I put the definition here, but you will see that bracket will enter later in the talk. And so what it is, you take just the Dirac bracket of the two symmetries. And here, what does it mean? It means that because your symmetry here are depending on the field of your theory, of the point of the phase space. So for example, psi r, you see that there is a eta dependence here. And it means that here I'm taking the variation of that Killing vector over the phase space. So it means that I have to take how this vector psi1 change when you act with the psi2. And if you compute this bracket, what you find is the following algebra. So let's analyze it. You have first, let's look at this t, so at the t component and the y component here. You see that if you look at the bracket, that is the diffeomorphism over S2, C2, sorry, because C2, I call it is the null cylinder parameterized by nu and phi. And that is the diffeomorphism of that cylinder here and here. And while W, it's the Weyl transformation, the Weyl transformation of this cylinder. And now we have this group of symmetry. We want to know if they are pure gauge or not, if they are or not. And for that, you need to look at the charge associated to them. In gravity, in gauge theory, you have the generalized Noether theorem that tells you that to any symmetry, you have a boundary charge that is associated to, so a codimension 2 charge. You know that in the when a global symmetry, Noether theorem tells you that to any symmetry you have a volume charge, and here because it's gauge, you will get a boundary charge. You can think of it, think on it at the electromagnetism case when you have the Gauss law. It's an integral over a boundary. And what we get is that if the Q is 0, it means that when you act with that symmetry on a state, nothing will change, and so it's pure gauge. While if the charge is non-zero, it means that the symmetry is large or physical. But however, there is a little problem in gravity is that you don't have a formula when give you this Q. You rather compute just a variation around a point in the phase space. So you take a point, a metric J, and you will compute the charge between this point and the infinitesimal variation over the phase space around that point. So that's why these delta are there. And here the boundary, so it's on R equals 0, but it's also at a fixed time that you compute it. And so that's the metric, and H is the variation around that metric. And here I have display you the formula. You can put all the ingredients in there and you find this result. So let's see what we have in that equation. So W, Y, and T were the symmetries, and you can see that they have, all of them have a charge attached to them. They all appear in the chart. It means that they are all large. That's the first point. And now let me give you a bit of a sense that what we have as an ingredient. So omega was the term in the metric proportional to d phi square. This gamma here, if you look, for example, if you take the BTZ black hole on those coordinates, you realize that this gamma is related to the surface gravity of the BTZ black hole. And if you take, obviously, the null hypersurface to be the horizon of that black hole. And the upsilon is related to G nu phi, so the fact that you co-rotate or not with the horizon. And the chi, it's related to the expansion of your null hypersurfaces. So you have a bit of a feeling of what those ingredients, and I choose to not write the full expression. They were pretty long, so if you want to see them, go to the paper, and yeah. So that's it. So now we have the charge, and as I was telling you, is those charge integrable or not? So can I integrate over the phase space, not over this space-time integral, but really over this delta? And what is important is because when the charge are integrable, it means that this Q, it exists, and it's really the Hamiltonian associated with the flow generated by that symmetry psi. And we will see that later, but when the charges are non-integrable, it means that they are related to the presence of a flux through the boundary. And we will see that a bit later in the 4D case, but the flux will be given by the non-integrable part of the charge. So,
can I ask
yeah.
a question? How do you arrive at the expression that you had for the, is it just a Noether charge that comes from the Noether theorem?
Yes.
And do you include the boundary terms in the action?
I have not fixed any ambiguities in the action. So here I use I computed the charge of in the higher wall prescription, and it's given, I mean, or the brand varnish brand will give the same answer, but it's true that you might be worried about some ambiguities in the action. And in this case, as we didn't impose any boundary condition, we cannot yet address these ambiguities in the action. I don't know.
But Celine?
Yes?
A boundary term wouldn't change the symplectic form, would it?
It depends which type. I mean, if you have this higher-wall ambiguity, this Y, and it might have an impact on the, because your symplectic potential, you can always add the D of something, and that might have an impact. But
that is true. Right.
And there is no reason of choosing one on another one, as I didn't put any boundary condition yet. So, yeah.
Okay. Thank you.
But so if you think physically, you might ask, but in 3D, we know that there is no local degrees of freedom. So what that flux could be, what does it represent? And so we actually realized that if you do a state-dependent redefinition of the symmetry generator, as we will do in a second, you can make those charges integrable, which physically makes sense because there is no proper flux, because there is no local degrees of freedom passing through. So let's see how it works. So that was the charge I just showed you. And if I define W hat, Y hat, and T hat in such a way, you can convince yourself that the charge will be written like that. And so now if you say that those hat symmetry generator are invariant over the phase space, I mean, it's quite straightforward that you can integrate the charge. And just a little, so it means that we have 3 charges, independent one, and that will be our boundary degrees of freedom, and that they will be so labeled by this omega, this epsilon, and this p. So omega was related to the term in d phi square in the metric, this one to the rotation of the coordinate with respect to the null surface, and p is related somehow to the expansion of your null hypersurface. So here I have found 3 boundary degrees of freedom, codimension 1, so I know that I'm the maximal case, so I have found the maximal realization of those 3 degrees of freedom. So that's what I was telling you that I was going to do. And just a little note that if the expansion is 0, what do you do? I mean, if you take a point of the phase space where the expansion is.
Okay, I think we just started again the recording, so you can continue. Just share the screen.
Okay. Oh, my screen is not shared. Okay, very good. So let me share my screen. Yes, is it?
Sorry, Celine, just to make sure I understand. So what you did, you pick some null hypersurface with some preferred coordinate system on it, and you look at the subgroup of the diffeomorphism group that leaves this coordinate choice invariant, and you found it's parameterized by some functions. And then, okay, I didn't manage to count how many functions you had, but is it a reduction of the number of functions that you find by demanding integrability?
Right now, there is no reduction on doing
because
that.
You're requiring that this T hat, W hat, and Y hat be invariant over your phase space. So
here I'm putting some condition on those functions. I mean, when you want to integrate the charge, you have to decide what is invariant or not. Okay. So yeah, when I integrate the charge, I'm making a choice there. That I agree that I'm reducing, I'm choosing what I keep fixed or not on the symmetry generator.
But as far as the number of functions that were parameterizing your subgroup of the diffeomorphism group is concerned, you're still having the same number of.
Yeah, I still have. I had 3, and I'm still having 3. I'm not. Yeah. Yes. So you might worry to divide it something by 0.
Sorry, I have a small question, Celine.
Yeah.
So it's related to Giuseppe's question. So you write a family of metrics and it's about adding boundary terms. So for example, are you worried that the variational principle will be satisfied for this family of metrics?
It's a very good question. And actually, so, okay, you might find that, okay, there is two answer, I want to say. If you want that you get a proper variational principle, so meaning that delta S equals 0, it means that you don't, when you do that, that will impose some boundary condition of your space, phase space. Mm-hmm. And you can show that there is a relation between the state dependence of your symmetry generator and the boundary condition. So imposing a boundary variational principle will link the what you constrain on the metric and what you constrain on your symmetry generator. So here I didn't do that. Why? Because actually when you have some open system, so when you have some flux through a surface, you don't have, I mean, delta S won't be 0.
Okay, so, you're considering you're adding fields and equations of motion have to be satisfied with the extra fields.
I mean, equation of motion will be satisfied, but the fact that you have some flux through the surface, I mean, delta S won't be 0. I mean, or you have to understand how to modify the variation principle in order to encounter by something that you're losing through the surface, which is not, I mean, to me, is not yet clear how you can deal with that. So that's why I'm not so worried about the variation principle, even though in 3D, I think we have to figure out exactly what we have. But in 4D, for example, I don't see why you should have one. So that's why it's interesting to disentangle the state dependence of the symmetry generator and on the metric. Is that?
Yeah, I see, okay. Thank you.
Just following up on that, could it be useful to talk instead of about the symplectic form? Because so if I understand correctly, if you want an open system, maybe the symplectic form will not be conserved, but you want to quantify the non-conservation in terms of the flux passing through the boundary. I guess if you impose the Dirichlet boundary conditions, that's guaranteeing that the symplectic form will be conserved, but she doesn't want to do that. And yes. Maybe there's some sort of useful way of parameterizing it.
Exactly. It's exactly that. And also I think it's, our work is interesting because you showing what is the most general setup. And after, if you, depending of the physical situation you will face, you can say, okay, I want to impose the Dirichlet boundary condition, and you can reduce the amount of symmetry and the boundary condition, and you will impose condition. So it's nice to start with the maximal one and after imposing extra condition, but yeah. Great, so yeah, so just comment if this guy is 0, you just don't do this change of basis. This one, you just keep t hat equal t, and you can still find integrable charges. Oh, where am I? Can you see? Yeah. Okay. So now, what is the charge algebra? Because that's the one where under which the state will be organized in the phase space. And so you can show that the charge algebra will be given when the charge are integrable by the charge of the bracket of the symmetry up to a central extension. So if you do this computation or setup, you realize that the charges in the integrable basis are given by this one. So the epsilon was related to the rotation, and so you have the S1, and the omega was the charge conjugated to the Weyl transformation, and P to the time translation in the old coordinates. And so that you get the Heisenberg algebra. And you have some, it's not a direct product, so you have some commutator, but we will see that, okay, I want you to focus on that part. And why I'm saying that, because here I found you one basis where the charges are integrable, but actually you might worry if there is other basis, and actually there is. And one basis that is really interesting is that what we call the fundamental basis. And why is so? So if you do, instead of using this upsilon, you use this S. And so you introduce new generator, the tilde, so 3 of them still in terms of this hat one. The charge will be written in such a way. And once again, if you decide that those tildes are invariant over the phase space, you find that the charge is integrable. And now if you compute the algebra of that charge, you really have Heisenberg in a direct sum with diff S1. So it means that as we go along, we'll see that anytime the charges are integrable, we argue that you can always find this fundamental basis. This fundamental basis is always accessible when you have a Heisenberg in direct sum with the diff S1. And we call it fundamental, general method. So in full generality, you can generate as many different charges as you want. So mu are the symmetry generator and qi all the charges. And you can change your charges and making a arbitrary function, a certain function of your charges and any of the derivative with respect to the angles that you have. And still you will have other charges and you can integrate them, but those q tilde don't necessarily form an algebra because depending on what you choose here. And in the paper, we have a discussion about what you can have and if you can have other Lie algebras and so on, but I have decided to not present it here. So if you want to see more about this general method to generate integrable basis, please have a look there. And I just want to show one example that when you start with this fundamental basis and you go from it to two currents algebra and a diff S1, so you do this change, and what you get is that this algebra of current, and once you get the current algebra, you can go to a Virasoro by a Sugawara construction. And here we even add this term. And this term, as you will proceed, will encounter for the central charge. So we even show that you can generate a central charge using this change of basis. So here I show you that you can reach the Virasoro algebra. You can also do a similar construction that you will get a BMS3 plus diff S1 algebra. And the question now is a bit what those different algebra represent physically. Here I show you on the algebraic point of view, I can construct all these integrable bases when the algebra is still integrable and everything is good. But the charge itself will be different. And so what does it represent and why you will choose one basis or another one, that's our open question.
Just to make sure, so what you actually found was a current algebra, and then you squared it to get Virasoro, but you didn't find Virasoro directly represented on the
exactly.
And the central charge, was it fixed, or you could make it whatever you wanted?
I can make it whatever I want because it's the parameter here that I use in my transformation of my charges.
I see.
But okay. Yeah, physically, I think there is a sense of why, how you choose these beta plus minus, when you proceed, but here I don't have any explanation of why that change of basis, what it will represent and which kind of central charge you will get.
So do you understand what it means to take the square of a generator, to take the square of J? Is it something like, could it be something like, okay, J is associated with something like asymptotic killing vectors? So when you square them to find Virasoro, could it be, I don't know, a killing tensor or something?
I don't know. On the geometry, I don't yet understand what does change of basis will do, because as I didn't impose any variational principle, I don't have a relation yet between my state dependence of my generator, that's what I'm changing, and what's happening in the metric. So right now, I can do that. No one forbids me to do that, but I don't understand yet what it implies. So I cannot tell you more. Okay. And I think it's a super interesting question. That's we're working on to try to understand what does it implies on the metric and why such algebra will appear more in that kind of problem or another one. because on the algebraic point of view, you can change from one to another one.
Yeah. Okay.
So just to recap the first part of the talk, I show you a boundary structure in which you can realize the maximal number of boundary degrees of freedom, show you this state-dependent redefinition of symmetry generator, while you can show that the charge are intrinsically integrable. And I give you 2 examples of different symmetry algebra that you can reach. And on the paper as well, you can find the case of 2-Einstein dilatant gravity. And I didn't present it here because it was the same philosophy, because you have no local degrees of freedom in that setup. So you also expect to only have boundary degrees of freedom. We have switched on the maximal number of them, which are the number of 2 codimension 1 function. And one of the bases that we found is this fundamental basis. So it's the Heisenberg algebra, because you have only in 2 dimensions. So you have just that part. So now let's move to 4D. Why is interesting? So you go to 4D, now you have bulk degrees of freedom. So you have gravitons, and still we expect those 4 degrees of freedom on the boundary. So once again, I put my null surface at r equal to 0. My coordinates are this time v, r, and xa, where a is the angle, so it's theta and phi. And I'm choosing this gauge once again. So that's my expansion of, my boundary structure is given by this guy. And to have a null hypersurface that relates this kappa to this u term. And once again, the eta here is just depending on the angle and the time. And all the function here, you expand it in power of r. But here, to avoid complicated formula, I have taken the rotating frame. So I will impose that this fa here is 0. Yeah, so that's an extra condition I put. So it will be easier to show you my point taking that setup. So once again, we look at the symmetry that preserves that structure. It is given by this translation in time, this Weil rescaling here, and the rotation parameter y. And now, because we are in the co-rotating frame, we lost the v dependence that we had before. And so the algebra, you have still t and y. Here you don't have the part when y is involved with t, because y doesn't have a v dependence, but still you have the diff C3, so of the cylinder plus the 2 sphere. And you have still the Weil part of the algebra. Once again, we compute the charge, and that is where the fun starts. So I'm defining that the determinant of my boundary metric, so of my angular part of the metric, to be omega square. And I introduce this NAB that I will call the shear tensor, or the news one. And it is traceless, and it's given by that. And so the expansion of your null hypersurface will be d v omega over omega. So this guy is really the shear of the null hypersurface. And I will justify why I call it news. And this gamma, it's related to the surface gravity when you take BTZ. Anyway, so the charge, we have the charge here. And so you can see that all those symmetry generators are large because they appear in the charge. And so they will label the boundary degrees of freedom, and we will have 4 of them, 2 being function of codimension 1, so v and xa, and 1 will be just, the epsilon here will just depend on xa, because we are in the co-rotating frame. But so let's look now about the integrability. So here I have displayed the charge again. So we can see, so if I take NAB equal to 0, and when this case happen, for example, it happens if you take this omega AB to be conformal to the 2 sphere. So in that case, NAB equals 0. And you can see that if this term is not there, I can define omega hat and t hat, and I don't change y, and the charge are in that form. And so if I choose the basis where those hat symmetry generator are invariant, those charges are integrable. Once again, if the expansion is 0, you don't change the t and you can still proceed. But now if you have NEB different of 0, actually, because NEB is traceless, you cannot build a scalar in which you can, use in this t hat to make this stuff integrable. There is no way of making this part, playing with this t hat to make this part integrable. So it means that really NEB is responsible for the fact that the charges are not integrable. And that is related to the fact that there is some flux through the horizon. And so that's why I have called it news, because this term really is the flux through the surface that you have. And so now my charges are not integrable anymore. So I cannot use the bracket I have used before, because I cannot write Q, I can only write delta Q. And so to compute still the algebra, a method has been proposed by Barnish and Troussard to use this modified bracket. So that was the old version. So the new version is that you will separate your delta Q between the integrable part and the non-integrable part. And you will compute the algebra of the integrable part of your charges. And that will be given by the charge of the bracket of your symmetry up to a central extension. But you have to add this flux part, this F, so the non-integrable part, to your algebra. And you can, doing so, because you separate between integrable and non-integrable, you have some ambiguities, because you have to do always the freedom to add the delta of n to your delta Q and separate between what is integrable, what you call integrable and what you call non-integrable. And if you have this ambiguity, you can see that these brackets will be invariant up to the modification of the central charge. And in our case, if you choose the separation between Q integrable and F in such a way, you find that the algebra of the charge will be the same as the one of the Killing vector, so the one I have shown you, without a central charge. So it means that you can pick the ambiguity to really display that the central charge in this case is 0. And why it's interesting to this bracket, because now we will see why the non-integrable is the flux, because if you have no central charge and if any quantity in the metric really transform under the time translation, just like is the time translation of that field, you can show quite easily that you obtain the generalized conservation equations. That means that the variation over the time of the integrable part of the charge is really given by the flux. So the non-integrable part, is given by the non-integrable part, and so that's why I call it flux during my presentation. Okay.
Sorry, just to understand. So if you require that the flux part is just proportional, so it vanishes when the news vanishes, does this fix the ambiguity or no?
If you are in the case where NEB equals 0,
mm-hmm.
you can write this based on the charge are integrable, so you don't have this ambiguity anymore because you have integrable charges now.
Exactly. So can't you fix the ambiguity such that it's proportional to NAB? Such that F only has terms that are proportional to NAB?
I actually have to see. Yeah, maybe it's possible. Maybe it's a good point. I have to. Yeah.
So in that case, if you did that, would the charge, is that the case where the central charge is 0?
I don't remember now. I have to check. But I will guess you're right, and that's
Okay.
Yes, I guess that's what. Just the F is just the news part. Yeah, that will make sense.
May I make a comment here?
Yeah.
If we can find an integrable basis, which we can, the answer is yes. So we can always, when n is 0, if we are in the integrable basis, we can always basically achieve what was just asked.
Okay, so then that could fix the ambiguity.
But we should be in an integrable basis.
When the charge is, I mean,
please
there's
go ahead.
no ambiguity when you have in an integral basis. Because
I think she meant if we can fix n by asking that f be proportional only to n.
Yeah, and I think the answer is yes, but I have not done the computation, so I have to check. But yes.
But, yeah, and I think here we are not in that case because f has terms that are not proportional to n.
Yeah, but depending on the transformation, maybe they cancel each other, and at the end of the day, it will be the case. But yeah, I think that has to check.
Actually, I think the answer is certainly yes, because we have checked and there exists some integrable basis when n is equal to 0. But here we are not in that basis.
Yes. Yeah. And just before going to the conclusion, I want to just give you a flavor of why when you impose further condition, you lose symmetries, and also to make a connection with previous work that have been done in the literature on near horizon conditions. So that was the metric element we start with. And for example, if you ask that this eta, instead of being an arbitrary function of v and the angles, you ask that to be 1. So it means that you ask that the variation of that guy over the phase space to be always 0. So that was his transformation law. So you see that if eta is 1, it imposes that w is related to your t. So it means that the Weil transformation, I mean, you have only, instead of having 4 generators, you only have 3, t and the 2 y's. So you're losing a symmetry generator, you're losing a charge, you're losing a boundary degrees of freedom by fixing that gauge. Another thing you might ask is like, physically, you're interested, for example, in black hole physics, and you want to impose that your generator of your horizon has a constant surface gravity, as it is the case in an isolated black hole. And so what does that imply? So that is the generator of your null hypersurface. And so if you compute the surface, its surface gravity is given by that. You ask that is 0, that the variation is 0 and that it's constant. What happened is that you have the t now is not an arbitrary function of v anymore. It has to satisfy that equation that I have solved here. So instead of having an arbitrary function of v and the angles, you have two function of the angles. And if you impose both in the same time 1 and 2 condition, you go back to the symmetry that were found by Donna et al. In their paper, where they use the same formalism that I have shown you now, and also some the symmetry you find in the Chandrasekhar Prabhu paper, where they use this another way of describing the null hypersurface with this universal structure.
So just to understand this eta, fixing it to 1, you don't have that freedom normally. So that's imposing a boundary condition on your.
I mean, if you can, I mean, by I mean, there is a diffeomorphism that put that to 1. You still have that freedom, preserving the gauge. So preserving GRR equals 0 and GRA equals 0. You still have, you can still use a symmetry to put that to 1. And so it means that if you had chosen eta to 1 beforehand, actually you have lost something on the way. I mean, you have lost the boundary degrees of freedom. So usually that's the condition when you put Gaussian null coordinates, you impose that, or Newmanian T gauge, you impose that this guy it's 1. Okay, so conclusion. So what have we done in this talk? We have switched on the maximum number of boundary degrees of freedom in 3D gravity. And so in general, we expect that we have the function of codimension 1. I've shown you that in the 3D case, there is always an integrable basis. And actually there is more than one. One being this fundamental basis when it's Heisenberg in direct sum with diff SD minus 2. That's what we were expecting. I mean, if there is no flux, I mean, no degrees, no bulk degrees of freedom, we're expecting that we can always find this basis. And in 4D, I have shown you, I hope I have convinced you that the presence of news of this share of the horizon will make the charge intrinsically non-integrable. So it means that you have really flux going through your null hypersurface. And also, and the last part I show you that choosing boundary condition or a gauge might kill some of the boundary degrees of freedom. And the counting I have give you is, it's interesting because it gives you what you can expect as the number of degrees of freedom, the boundary degrees of freedom that you can have, so you can know if you choose a proper gauge or not, and if you're losing some information or not. So one of the proposals we're making is that when there is no degrees of freedom, local degrees of freedom, you have this fundamental basis, and that we're working on the proof. And we have a lot of further questions, as I was telling you, to finish, to continue on that project. So that what are these bases represent physically? That was Monica, Stefan, and Giuseppe question. How we can link the choose of basis with the boundary condition, really with what is kept fixed or not on the metric. So what do they represent? And also I was speaking about surfaces in the bulk, and there is this class of particular surfaces that, for example, asymptotically null infinity and so on, where the metric diverges. And so there is a bit, you have to give a proper treatment to those questions, because you have other not problems, but other features that appear. But I think it will, at the end of the day, will fall in the same big picture, but we have to give a careful treatment of those surfaces.
Don't you expect that the essential difference between a null surface in the middle of the bulk and one at infinity is that at infinity you don't have an arbitrary choice of integrable charges?
Maybe because you, for example, because you want your time to be part of the symmetry generator, so that fixes you that you don't want to change this T generator. You want to keep the translation. You have a sense of what is exactly the time. So maybe you want to keep that on your symmetry generator, so that.
And also you're not allowed to fluctuate certain things at infinity because they lead to infinite charges, which doesn't happen in the middle.
How to treat the point is like some charges will be divergent, so you have to fix boundary condition. So that will, exactly. So I think because you can have divergences, you have to be careful about what you're doing. But that's an open treatment question. Yes, and finally, I want to emphasize that all the charge I have shown you have an arbitrary V dependence. That usually is not the case. And it means that even though my charges are integrable, they are not conserved. When I take dt of my charges, I have something and I don't know what I have. And it's because I have not given this variation in principle, I have not given you the Hamiltonian that will govern the dynamics of my boundary degrees of freedom that will impose further condition. So that's why you have this arbitrary V dependence. And so that's also something we have to push further away, that because you can choose arbitrarily the dynamics on your boundary. So once you have decided what is the boundary Hamiltonian, you will have, the charge will be or conserved, or will have a clear evolution on the time. A defined evolution of the time. And also what is an important question also is like in the basis where the charges are not integrable, like when I started in the 3D case, I was in the base for my symmetry generator when the charge was not integrable. And the question is like, what this apparent flux, so it's a flux that is not related to local degrees of freedom, but if I want to keep that basis when I don't change my symmetry generator, what this flux represent, what it is. So that's another question we have to address, and we're working on that as well. And also maybe see if all what we have done are applied to time-like surfaces, which I believe will will be the same structure, but still maybe there will be some like technical details that will change the story. So thanks a lot for your attention.
Thanks a lot, Celine. Questions? Sorry, you didn't quite a few, but more questions?
I may have one.
Sure.
Celine, what you define as like your news look like it's not outgoing wave. Like if I wanted to interpret, it looks like it would correspond to gravitational wave on the surface, if I may do something like that. So physically, we don't expect that to have this kind of wave on the black hole, right? Because they would decay very rapidly by going inside. And so is it because you consider your surface as a boundary instead of having just an horizon inside the global space-time that you may have this, or should they be killed also by your equation of motion?
Very good question. And yeah, I think I mean, what I can say is that the 4D case, we have that part, but the non-integrability, but we are working on the what is physically what is happening on the story with gravitational wave and so on. But this NAB, it's capturing the gravitational wave for sure. So because you have, okay. Yes, about physical process in precisely, I don't know, but their NAB is really this traceless transverse part of the angular metric, which is usually there that you have the gravitational wave. So that's what I'm expecting to be there. But about more physical process, I'm afraid I cannot say anything more right now. So, yeah.
Questions?
Can I ask a question?
Yes.
So at some point I decoupled because I had a technical problem, but at some point I think you said that by changing basis, so by doing a field-dependent redefinition of the symmetry parameters, you obtain a different algebra, or is it the same as the initial one?
It's a different one because
okay.
Because the field are state dependent. It's a state dependent definition. So yeah. When you use the adjust bracket, you have this part when you have to take into account the variation of your generator with respect to the phase space variation, and that will change the algebra.
And so if I compare the initial one to the next one, what was the initial one and what and the I remember the last one.
Initial one was a semi-direct product between Heisenberg and diffs1.
Mm-hmm.
And one of the bases you can reach is that when you have a direct product between Heisenberg and diffs1. So it seems to see that when you have no flux, you have always this structure, and that also was, I mean, I think it's related also to work of Carlip on the horizon, when you have this structure that emerge also like on the null hypersurface. So yeah.
Okay, thank you.
More questions?
I had some questions. So there's a lot of work about. So first of all, if I understand correctly, there was nothing special about your surface being a horizon or not, or being a boundary. So in particular, I could consider a family of such surfaces, let's say spheres of increasing size, and then I could have a symmetry algebra on one. And then if I get a bit further, I can choose my integrable hatted variables to be slightly different and get a different symmetry algebra. Mm-hmm. So there doesn't seem to be anything fixed about the symmetry algebra, mm-hmm. which sounds completely correct. I mean, it's just some subgroup of the diffeomorphism group. So how do you interpret all these? I think it's work by Strominger and the late Hawking and so on, about near horizon symmetries of Kerr and trying to get Virasoro algebra with a specific center charge and stuff like that.
Yeah. Yeah, so they will have, it's a bit a different approach where they look at in the bifurcation surface of a black hole, and they don't write boundary condition as like, as I was showing here, like a boundary structure that have to be preserved. They take the Kerr black hole, they take one point and they look around a perturbation around it. So they will just look at symmetry that just preserve Kerr, but they are not showing you a whole phase space because they're just keeping that point and looking at the symmetry on that point. So it's not clear if yet if they're what they are doing, it's consistent when you take a full phase space, a full expansion of the metric with arbitrary function in there. So, but I know
your work seems to suggest that if they make slightly different choices, your work seems to suggest that there exists a choice that will give something that you would like, in particular central charge equal, I don't know, 12J.
Yeah.
But there could be equally well-motivated physical choices that would give a completely different algebra with a different central charge.
Yes, yes. But the question is, I mean, here in their case, they really choose the Kerr black hole in a certain type of coordinates, and they really don't play with this field dependence redefinition and so on. So still we have to see how it connects with their result. And I think it's indeed a super interesting question to see if they have really something else as in the philosophy, because as I was telling you, they are not presenting like a really fall off of the metric. They are taking just one point and looking around one point of the phase space. So I have to see if that what we do, we can reproduce, we can reach what they have done, or if it's really conceptually two different approaches. But
I
yeah.
see, but in particular for you, there's nothing special about being a horizon, or even if you had a bifurcation surface.
I think if you have a bifurcation surface, you want to preserve that structure of being a bifurcation surface, so you have to impose more condition on your phase space, as I was doing when I asked constant surface gravity, for example. You have some extra structure to
I see, but do you think this extra structure would be sufficient to actually fix the algebra? Like if you just impose having a bifurcation surface, and
I think you will restrict it, but probably you will still have freedom to redefine some generator state dependently in the state dependent way, because we still have symmetries. But I don't know what you will. Yeah.
I mean that sounds totally reasonable.
Mm-hmm.
So just to make a comment, you said at some point that the charges are not conserved. Which confused me, because I thought that the moment that the symplectic form evaluated on your null surface is 0, then the charges are conserved.
Yeah, but the point is so conserved implies integrable, but integrable doesn't imply conserved.
But isn't the symplectic form 0, like in the no news case?
No.
I see. So this is why they're not conserved.
Because I didn't have looked at the variation principle, so I didn't, yeah, exactly. But we have still the integrable, so this generator contracted with the symplectic form will be 0.
And just a final comment about asymptotic infinity. So my understanding of how, or my intuition of how things happen is that at asymptotic infinity, you have a preferred set of boundary conditions, just because things can have infinite energy, and that's unphysical to allow.
Mm-hmm.
And then I would expect that actually your symmetry group, you have a unique choice.
Yeah, that might be the case, although...
I mean, you might have, for example, in ADS3, if you play a lot, you can have mixed boundary conditions, or you can have some other stuff, you can play a bit, but generally, you won't have a lot of choice at infinity, whereas in the middle of the space-time, because things don't blow up, you would have an arbitrariness.
Yes. But yes, I think, I mean, I agree with your intuition, though. I'm working on it to see if really it is the case, or if there is maybe some unexpected freedom, or what is to ask that delta, I mean, really that the variation in principle hold. I mean, maybe you want some, I mean, to allow for flux, give you maybe some freedom about what you can do or not. So I agree with your intuition, but still I want to see it properly written.
Okay, sounds great. Thank you.
Make a comment here.
Yeah.
Actually, for the ADS3 case, there is the work of Grumiller and Regler, where they have considered the most general set of boundary conditions. And what they get is 2 copies of SL2R current algebras.
Yeah, I know. I think ADS3 is a is a case where too many things work. But if you take a normal spacetime like flat, asymptotically flat 4D, I don't think many choices should be allowed.
But I think based on what we have already done, that there's a bigger algebra than BMS4, which is possible. For example, you can replace the 2 Virasoro parts of the BMS4 with full diffeomorphisms on a 2-dimensional surface or 2-dimensional sphere in this case. And I think you can still extend the super translation part by what I would call super scalings, as we had in this 3-dimensional example. So I think BMS4 algebra could be extended in 2 different ways.
Okay, thanks.
Yeah, I have a follow-up questions on Monica's first question relating to Kerr and the work of Hawking, Parris, Frominger. So in their case, in order to get this nice relation between the central charge and the angular momentum, they had these Wald-Zupas counter terms. And I'm wondering if in your formalism, this ambiguity gets resolved, or what's the story?
Yeah, thanks. It's a very interesting question. So the Wald-Zupas procedure, I mean, relies on the fact that you can choose in your phase space one point where the flux is 0. You have to find the 0 of energies. I mean, the flux is 0 and you can integrate over. In this case, because the flux, there is no point when the flux is 0 because it's, I mean, one part of the flux is proportional to this omega that is the determinant of the angular part of the metric. And therefore it was, in our case, the Wald-Zupas procedure, we couldn't apply it, like we couldn't apply the mechanism because we don't have this point where the flux is 0. So I think that's why the modified bracket, was helpful, because the fact that we see that the central charge up to an ambiguity was 0, that helped us to fix the ambiguity and to choose what is the part that is the flux and what is the integrable part of the charge, because that was all the game of Wald-Zupas. Though also I have another comment to make about the work of Hawking, Parris, Frominger. They seems to play with that ambiguity, the fact that you can add something to the symplectic form to modify the charge and to get the answer that they might have wished for. So I know that recently Speranza, his collaborator, have been working on making that prescription more robust about this Wald-Zupas term, but yeah, I'm not sure about which term you can add. And when, I mean, you have so much freedom when you can add term to the symplectic form. So which one is the correct one and so on. I mean, Wald-Zupas give a correct prescription, I mean, a well-justified prescription in the case of asymptotically flat spacetime, but we couldn't apply it to our case. And so, yeah, so it has to be retuned a bit, I think. I mean, or generalized.
The ambiguity that it might not be the unique counter term that you can add will remain.
Yes, I think until you fix, when you fix a variational principle and some boundary condition, you may have justification of, but why is that prescription? Or you can argue on it, but in full generality, I would say that you have this one, yeah. It's a case-by-case problem.
But that raises the question, if you didn't know already which relation for the central charge you wanted to have in this particular case, and the question is, how do you choose the counterterm?
Yeah, it's yes, indeed. Yeah. But here we were lucky because we find it is trivially 0. I mean, it's equivalent to a 0 one, so it makes sense that it's this one. And maybe in other cases you have the central charge that is, I mean, even in Virasoro you can write your central charge in different ways. So mean, you can, I mean, you can find it, but you can still write your algebra a bit differently. And yeah, you know, you can switch your generator. So yeah.
Thanks.
More questions? Okay, if not, well, thanks a lot, Celine, for this very interesting talk and for answering many questions. So yeah, thank you very much.
Thank you for the invitation. It was very nice.
Hopefully next time.
By the way, Miguel, I
person.
wanted to ask some questions post the talk, if Celine is okay with it.
Yeah, sure.
And you don't close the session.
Sure,
I'm sorry, it's Razvan who has the session.
No. Anybody can. We can record or we can stop recording, and
maybe we should stop recording. Yeah.
Okay.
So stop recording.